We're now going to look at our new potential energy function, negative g mass of Earth, mass of the other object in the problem, divided by little r, both as a mathematical expression in the equation and the graphical representation of it. So what we have shown here, I have it highlighted in yellow, but you can either highlight it or darken it in or color it up how you want. We can see that since our potential energy values are now all negative, that the largest, the maximum, and this is important because the maximum potential energy that we now get is zero valued. I know that's a pain because we don't normally think of zero as a maximum, but hopefully you remember that fundamentally the only thing that ever has physical meaning is the change in potential energy. So delta U equals physical meaning, right? So without a delta U, we can't make any calculation or any understanding of what is going on in a problem. So the fact that they're all negative is fine, and as it says here, we are still increasing potential energy when we go up and decreasing potential energy when we go down. We do have to be careful because numerically we'll calculate a bigger number when we go down, right? The furthest we can go down, if we want to understand this graph, little r equals the Earth is here, the center of the Earth is here, so we come out to the surface of the Earth. The biggest negative potential energy, so it's the smallest, it's the lowest on our number line, will be at the surface of the Earth. So smallest potential energy out here, largest potential energy way out here at infinity. And as it says here, kinetic plus potential equals kinetic plus potential, still good. Our marble analogy, still good. So there's a lot that's nice here in that the basic structure we've put in place to understand the potential energy functions does not change at all. So please take a moment, pause here if you have to, annotate your notes, and we're going to take a look at a specific example of utilizing our new potential energy function. Okay, so here we are looking at what is called escape velocity, and as it says, to infinity and beyond, because what we are looking at in understanding escape velocity in maybe a simpler language is to say, how fast would you have to throw a ball, right? That's going to be our escape velocity, fast. How fast would you have to throw it in order for it to go to infinity? That is, to have the ball go up and never come down. Well, it's a very easy calculation now for us to make because we have our law for universal gravitation. We have kinetic plus potential equals kinetic plus potential. Our initial kinetic energy is going to be down here, right at the little r equals the surface of the Earth. Our final potential energy is going to be 0. We're going to throw it with just enough speed to get out here to infinity, and it comes to a stop. Okay, so our final kinetic energy is 0. Our final potential energy is now maximum valued, right? So remember our PE max, we're going to have maximum potential energy out here, right? So that's max potential energy, 0 joules equals max potential energy out at infinity. So we have a very simple equation. Now our initial potential energy is going to be capital G, capital M, little m over the radius of the Earth. And you can think of using 1 kilogram, like a 1 I thought in terms of thought analysis. Let's use a 1 kilogram mass. But whether we think of it as a 1 kilogram mass or we factor the m's out and then 0 divided by m is 0, or we cancel the m's out here, that velocity that we're calculating will be the same for any mass. Just the larger the mass, the harder it is to get it up to this speed of 11,172 meters per second, which we can see is 25,137 miles per hour. So very, very fast. And I have just an interesting little example here for us to look at. I think it's illustrative of how the actual potential energy function for the Earth works by looking at how hard was it to get to the moon. Because the moon is not quite as hard as infinity. The moon is not at infinity. The moon is 238,000 miles away. So when we calculate the potential energy value for the moon, right, if we use our capital G mass of the moon, again, I use a 1 kilogram mass here as my representative mass, divided by the radius of the moon to get a potential energy function at the surface of the moon. 2.83 times 10 to the 6 gives us our joule value there. So that is going to give us the final potential energy function value we need to achieve since we're not going to infinity. Our initial potential energy is, again, the potential energy at the surface of the Earth for that 1 kilogram mass. And we can see that to get to the moon, we are still at 24,559 miles per hour. So really, most of the work, the reason you need that high speed is because it's hard to get away from the surface of the Earth initially. The further you get, the easier it is to get further away. So even though the moon is not nearly at infinity, you still have to achieve an extremely high rate of speed in order to get it to the moon based on this simplified type of calculation that we are doing. So the most important thing for us is to understand the kinetic plus potential equals kinetic plus potential, and the fact that we will only ever get zero final potential energy when we are actually at infinity. Other than that, we will have both the final potential energy and the initial potential energy as part of our calculations. So please take a moment, again, to make sure you have everything completely annotated, and we will take a look at utilizing our new universal gravitational potential energy to calculate speeds at different points away from the Earth.